Hi, David Abonic Turtle with an illustration of how we calculate bond convexity, which is a more advanced bond topic. So I attached the spreadsheet next to the video on the website if you'd like to take a look at the calculations. This is a little bit harder than bond duration. And I'm going to look at convexity quickly from two different perspectives. But first here I've got a 30-year zero coupon bond, so I deliberately chose a long maturity bond because they have greater convexity. And then I plotted the familiar price yield curve for the bond. That is to say, as we move to the right here, this is the yield. As yield increases, the price of this 30-year zero coupon bond decreases. That's in blue. That's the price yield plot for the bond. And here at 5% yield, I've plotted the tangency line, which would be really, the slope of that line would be dollar duration, and it really highlights for us that the price yield curve for a bond is not linear. So this curvature is really captured, we capture most of it with the convexity measure. So this high degree of curvature here reflects a bond that has high convexity. Why does this matter? Well, think about if you were long this bond or owned this bond. Convexity is your friend in this case, because here, imagine starting at 5%. If rates go down, the price of the bond goes up, but notice duration just tells us about the linear behavior of that. And notice you're benefiting here with incremental upside due to the curvature as the yields go down. On the other hand, if yields go up, notice the red line here describes where we would be under a linear relationship, but as yields go up, bond price does go down, but not as much as they would under the red line. So actually convexity is your friend even on the downside because it's mitigating the loss. So being long the bond is generally to like the convexity. Now, in order to do a more realistic example, I'm going to use a 5-year bond with a 4% coupon. My bond is shorter maturity now with a coupon, so I'm not going to get as much convexity, but you can see the blue line still captures convexity. And this is the first perspective that, to put it very simply, treats convexity as time squared, or specifically convexity is the weighted average of maturity squares of the bond. So here, assumptions: bond par of 100, $4 coupon, paid semi-annually, so that's 2 years every 6 months, and I'm going to assume a yield of 5%. So you can see here I'm plotting out the 6-month times, 6 months, 1 year, 1 and 18 months, 2 years, and then each of the coupon cash flows. $2 is half of the $4 coupon. Final cash flow is here. In this column, I compute the present value of those cash flows. This is probably familiar because the sum of the present value of all the cash flows gets me the model price of the bond. This bond has a price of $95.62 at a 5% yield. It is less than par, which is consistent with the fact that I have a coupon that's less than the yield. And in this column here, I've got the calculations that lead to the Macaulay duration, which to say, you can look, this is pretty simple or pretty straightforward here. I multiply the time or term, 1 year, times the present value of the cash flow. So basically, I'm computing here the weighted average maturity of the bond. But what are the weights? Well, the weights, the present values of the cash flows. So if I sum all of those, I get this number, and then, so I have the sum of this column, and if I divide that by the price of the bond, you can see that's what I've got right here. My point here is not to illustrate Macaulay duration. I've got other videos for that. But you can see if I divide this by the price of the bond, I get 4.57. I'm going to remove that dollar sign because it's not really in dollars. We sometimes say this is in years. I get the Macaulay duration of 4.57 for this bond, and it's less than the maturity of 5 years. Okay, so here's the convexity column, and here's the key idea. Try not to worry about the plus 0.5. That falls out because convexity is a second derivative, or dollar convexity is a second derivative. Convexity is a function of the second derivative. So this ends up being a function of the derivative, but you can see what I've got here is it's like duration in the sense that we do take the present value of the cash flow. That really is the weighting function, and we multiply by the time. Here's the 1.25 or 18 months. But we multiply by time again, or almost time again. You can see we've got this C10 times C10 plus a half is basically squaring the term, or squaring the maturity, and we're doing that for each of these. And so that's why I say convexity is really time squared, or specifically the weighted average of maturity squares of the bond. So in this column, we're effectively squaring all of these maturities because they each correspond to a cash flow. If we summarize that here, and then finally the convexity ends up being very similar. There's a little bit of an adjustment factor here, but basically we're taking this summation here, which effectively squared all these maturities, one for each cash flow, and divide it by the price of the bond. And we end up getting the convexity. In this case, 23.19 is the convexity and really captures most of that curvature in the bond. That's the first perspective, again, to treat convexity as the weighted average of maturity squared, squaring time being the important concept. Now, if we look at the second perspective quickly, this focuses on convexity being a second derivative. And here, I just zoomed out on our price line. And if I'll remind that duration, or dollar duration, is specifically the slope of that straight line. Dollar duration is the first derivative, the slope of the point of tangency on the price yield curve. So if dollar duration is the first derivative, dollar convexity is the second derivative. It is the rate of change of dollar duration, such that if the line has no convexity, if it's a straight line, there's no change in dollar duration, and we would have convexity, we would have dollar convexity and convexity of 0. That's not the case here. So in this case, instead of doing that analytical approach like I did before, I'm straight out repricing the bond. Here's the bond at 5%. That bond price, same as before, is $95.62. And then here is my first derivative, or dollar duration, at 5%. So really, it's really difficult to see here, but at 5%, it's the slope of that tangency line. And you can see it's a big negative number. And the formula here is really just a familiar rise over run. We've got here C19 minus C18 is the change in bond price. That's the rise over the change in the yield, which is the run here. And I get a big negative number for the negative slope of the point of tangency. So here's the dollar duration at 5%. And then I do the same thing, the calculation explicitly of the slope, rise over run, at 5 plus 1 basis point, 5.01%. There's the dollar duration. If this were a straight line, the slope would be constant. It's not. Here's the slope at 5.01%. So here we have dollar duration at 5%. Here we have dollar duration at 5.01%. Convexity is the rate of change of the dollar duration here. It's the second derivative, or rate of change of the first derivative. And so in this case, it's also just a rise over run. What's the change in my dollar duration as I move from 5% to 5.01%? And here we get a big number. That's dollar convexity, such that if I divide that by the price, I take the dollar convexity divided by the bond price here. Notice I get the convexity 23.19, same number I got before. And it's non-zero because there is convexity or curvature in this line. So that's the second way to look at it. You can see sort of the brute force. I went at the convexity directly. Up here, if you'd like to take a look at the open the spreadsheet, you can see how we apply the convexity as that second order approximation. So this is David Harper, the Bionic Turtle. Thanks for your time.